All right. Just waiting for the stream to start. Okay. Well, welcome back to Advent of Code. Today is day 8, and guess if it looks like the stream has started. Looks like we're good to go. Let's get rolling. Day 8, handheld halting. I should turn off notifications. There we go. Your flight to the major airline hub reaches cruising altitude without incident. Good. Well, you consider checking your in-flight menu for one of those drinks that come with a little umbrella. That sounds good. You are interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code. Of course, your puzzle input of the device. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Okay, so this looks like assembly basically. It's cool. Each instruction consists of one operation and an argument. Okay. ACC increases or decreases a single global value called the accumulator by the value given in the argument. Would increase the accumulator by 7. Okay, the accumulator starts at 0. After an ACC instruction, the instruction immediately below it is executed next. Okay, so it just goes down. Jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the jump instruction. For example, jump +2 would skip the next instruction. Jump +1 would continue to the instruction immediately below it. And jump -20 would cause the instruction 20 lines above to be executed next. NOP stands for no operation. No op, it does nothing. The instruction immediately below it is executed next. For example, considering the following program, okay, got a NOP, accumulator +1, jump +4, so 1, 2, 3, 4, accumulator +1, jump -4, so 1, 2, 3, 4, accumulator +3. Okay, those, yeah, this is what we're doing. +3, jump, okay, first, no, okay. Causes the program to continue back to the first accumulator +1 and jumps. It's the next instruction. Okay, it's an infinite loop. With the sequence of jumps, the program will run on forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Okay, immediately before the program would run an instruction a second time, the value in the accumulator is 5. So run your copy of the boot code immediately before any instruction is executed a second time. What value is in the accumulator? Okay. Well, that's interesting. So basically we just have an accumulator. That's the variable we're tracking. We also presumably will track our position in the code. And no op does nothing. That's it. It's ack, jump, and no op. Okay. Cool. All right, let's kick this off, and we'll talk about how to model this. New folder. So day 08. New file. 1.lit coffee. All right. Day 8. Handheld halting. So this is our input. So what we'll do is we will capture this input. Okay, these instructions are visited in this order. We'll just mark this as a plain text block. Okay, so we're gonna have our usual suspects. We're gonna have definitions. We're gonna have tests, and we're gonna have a section where we just run it. Cool. So how are we going to model this? So what we're going to do is we're going to take this input in, and effectively, I think what we're going to do is we're going to make an array out of it. That seems sort of like, oops, kind of a no-brainer. And then we're going to process these one at a time. Because it's an array, we're going to keep the entire array of instructions. We're going to need the array, and we're going to need to know which instruction we're currently sort of like operating on. So, you know, we'll start here, then we'll go to the next one, then we'll go to the next one, then we'll go to the next one, etc. So we're going to have effectively a pointer, and we're going to have an array of instructions. And then we also need to track the accumulator. So we could do this a couple of ways. We could use a while loop. Oh, I guess that's the other thing we need to do is we need to track which instructions we've read before. So we need to track a couple things. We need to track the accumulator. We need to track the pointer, and this is like which instruction we're working on, and we need to track a list of seen or used instructions, and that's really it. So how could we do this? We could have sort of like a recursive function that takes all of these arguments, including the list of instructions, or I guess we can call them steps. This can be step, and a list of used steps. Let's call them steps. It's easier to type. So we could have a recursive function that effectively passes all of these things in, and then for every step, it just sort of like does another thing. Calls the function with the current state, which is these things, and then calculates the next state and calls that. So we could do that. We could also run it in a loop. So we could do like a while loop. We could also create a class to track these things and call next in a loop. That would also work. Let's just do a simple. Maybe we'll do one simple function with a loop. So we'll have go. And what do we have? We have steps. Oops. This is going to be our list of steps. And we're going to have the accumulator, which defaults to 0. We're going to have the step, which defaults to 0. This is the step we're starting on. It's an offset of 0. And then I guess we'll say seen. So these are the used steps. It's going to be empty. So really, steps is the first thing that we're going to populate, and that's going to be our input here. So these steps, each step is going to have, we're going to need to parse the step. And this is going to have a line, and the line is a string. So that line is going to look like this. We're going to have, oops, we're going to have the name and then a value, like a positive or negative value. So we'll be able to split this apart. We'll be able to use parse float or something to parse that. So we've already got our input. Let's parse this line. So this is going to be instruction, and then arg. Okay, equals, and then we're going to blow this apart. So this is going to be word 3. Guess we should anchor these just to be safe. So that's 3 word characters followed by a space, and then followed by assign, followed by a digit, one or more digits. Okay, so this is going to be our first capture group, and then this is going to be our second capture group. So let's see what this looks like. This is dot match, and yeah, we don't have to global or anything. So let's see what this gives us. Let's just jump down here and log this. So let's get our old friends back. Log and assert. And assert equals require assert, and then we can log that. So it's angry. Match is not a function. Oh, it's exec. Is that what it is? Yeah, okay. So we got no-op plus 0. So we've got our instruction, and so let's grab that, and we'll say log instruction and parse float arg. So we got no-op and 0. Let's try a couple more. Let's try this ACK -99 just to make sure that we can handle negatives and we can handle multiple digits. ACK -99. Okay, cool. So this is our parse step. I don't know if we, and this is going to exec on the line. So parse step is going to have these instruction args, and we're going to return those as an array, and we're going to parse float. Actually, we'll split it up like this so it's more readable. There you go. So it's going to return an array with the instruction and parse float of the arg. Cool. So I guess what we could do is we could just map through our input and verify very quickly that these all look good. So let's do that. Say input split. What are we splitting on? New line. For line in, and we will log parse step line. Okay, so this is what we get back. No-op 1 or no-op 0, accumulator 1, jump 4, accumulator 3, jump -3, accumulator -99, accumulator 1, jump -4, accumulator 6. Okay, so this is all working. So we've got our parse step, and our return condition, when we're in this function, what we want to do is we want to return from this, let's call this run, because I feel like it's better than go. Okay, so when we're in this run function, basically what we're going to do is we're going to pass through our steps, and we're gonna evaluate the step at our current step. So steps, step. Oops. So this is going to be the line that we're evaluating, and we want to parse that line. And what we're going to get back is we're going to get back the instruction, and we're going to get the arg back. So this is what this is going to do. So we're going to parse the step into the instruction and the argument. And then we need to, let's look at this, parse it, and then evaluate it. And I guess, so this is the question, what are we going to do here to evaluate it? And I guess the other thing we need to do is we need to, are we done? We need to check and see if we're done. So we want to see if the step that we're on has already been run. So if step in scene, and then we want to return, they want us to return the value of the accumulator. Return ACK if step in scene. And so what could we do? We could either run this recursively. We could call this function again and again and again. So every state of the run loop or whatever gets its own function. Or we could run it in a loop, and we could just track the state as we go. So I guess what we want to do is we want to, yeah, let's try that. All true. So we're just gonna loop through this, and it will return from the function when that's when it sees its step again. So we want to evaluate it. So what does that mean? That means that we're going to switch on the instruction when accumulator, we want to ACK equals ACK plus equals to the argument. So we're going to add the accumulator to the argument. And then, oh yeah, after an accumulator instruction, we want to step plus equals 1. What else do we have? When jump. So jump, we don't automatically step after the jump because jump steps for us. We want to step plus equals to arg. And then what else do we have? We had no op. Else. So what we could do actually is a no op just goes to the next step. So what we could do, since they all add 1, we could say step is arg minus 1, and then we can remove it from there. And then, so that's not, well, yeah, I guess that's it. Else nothing. So a no op just does nothing, and then we always step. That's, I feel like that's more confusing. So this is going to switch on our instruction, and then that's it. It's going to loop. So, oh, and we need to add scene to, we need to add this step to the scene. So after we're done all this stuff, we're going to scene dot push step, whatever new step we're on. So let's see if this still compiles. It does. Okay, cool. So what do they want us to do? They want us to, okay, they want us to see that the accumulator is 5. They want us to assert that the accumulator is 5. Okay, so assert 5 is run input. Okay, so let's see if that's true. It is not true. Object null is not iterable. So this is on line 69. So, interesting. So it failed to parse the line. So steps. Oh, you know, it's because I'm passing in text here instead of input split instead of an array. Okay. So now, different problem. False equals true. So let's find out what run input is. Log, oops, and see what it says. It says 0. So 0 is what we get. So why is 0 what we get? So what we could do is we could just say, so until step in scene, and then we can put turn accumulator down here. Whoops. Whoops. There we go. So what we'll do is we'll put this after the loop. Okay, so it's still saying false equals true. It's still not doing anything. So let's throw some logs in here. Excuse me. Let's log step, and let's log instruction and arg. Okay, and we'll see some steps that it's doing. So it's seeing step 0. It's seeing no op. 0, good. Oh, because I don't have that else for no op. Yeah, of course. Okay. All right, so it did probably more stuff that time. It didn't. Okay. So it's logging step 0. It's logging no op, and then it's switching on the instruction, which is no op. So it should have gotten here. Should have added 1 to step, and then it should have pushed. Let's log step here again. So now step is 1, and then until step in scene. And then, well, immediately what it did here is it logged step again and logged step as 0. So that's super weird. Why did it do that? Where is it logging this 0? It's logging here, and then instruction argument. So it keeps running. So it runs no op, and then it finds no op has been in scene, and then it gets out. That's very weird. And then it asserts something. Is it returning already? Is that what's going on? Oh, okay. So it's doing that assertion. Okay. So step is now in scene. So okay. So we're adding the new step, right? Okay, so we need to do this earlier. We need to push the current step that we're on up here, and then right. So what I was doing here is I was writing down the steps we've seen, and then I was restarting and seeing that the step we just calculated was the one that we've already seen. So that's not very clever. So let's try that 5. So that's exactly what we want. So record it, parse it, evaluate it, bop it. Cool. Assert. We can get out of that. Oops. And then run. And then this is what we want to run. And instead of input, I guess, you know what, steps is going to be, it's going to be this, so we should just input split. I guess we can, let's call this program, and then steps equals okay. And then we can run the input. So we still get assert 5, and then, right, we're gonna require the input. Okay, cool. So let's grab our input and run that. Input dot coffee. And module.exports equals, that's not it. Copy, paste. All right. Survey says 2025. All right, let's see if that's what they're expecting. Survey says, yes, you are 1 gold star closer to saving your vacation. Woohoo! Continue to part 2. Okay, so let's copy this and we'll paste it in a new file. Oops, no, not coffee, lit coffee. Okay, part 2. Okay, so let's read this before we do anything else. That's always my problem, is I make assumptions about what part 2 is, and then I fail to read exactly what we should be doing. Okay, so after some careful analysis, you believe that exactly one instruction is corrupted. Uh-oh. Somewhere in the program, either a jump is supposed to be a no-op, or a no-op is supposed to be a jump. Okay, no accumulator instructions were harmed. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. Okay, so interesting. So when we're supposed to get to the end, okay, and that's how we're supposed to terminate. By changing exactly one jump or no-op, you can repair the boot code and make it terminate correctly. So for example, considering the following program, if you change the first instruction from a no-op to a jump, it would create a single instruction infinite loop. Yeah. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. However, if you change the second to last instruction from jump -4 to no-op -4, the program terminates. The instructions are visited in this order. After the last instruction, the program terminates by attempting to run the instruction below the last instruction in the file. With this change, after the program terminates, the accumulator contains the value 8. Fix the program so it terminates normally by changing exactly one jump to no-op or no-op to jump. What is the value of the accumulator after the program terminates? So this is interesting. How are we going to find out which, like, presumably we have to programmatically figure out which instruction to change. What we could do is we could just try different permutations of changing no-ops to jumps and jumps to no-ops and vice versa. And they always want exactly one change. So if there's, 100 of those instructions, it would be like 100 loops that we'd have to, or 100 attempts to make, which isn't terrible. I mean, computers are fast, we can do that. I wonder if there's a smarter way to go about doing it. Maybe what we could do is we could run the program, and when it gets into an infinite loop, what we could do is we could change maybe the last no-op or last jump command that it saw to see if maybe it can back out. I mean, we could probably do that, and that might be a smart way to do it, but it's probably not a safe way to do it. I think maybe the safest way is just to find all the jump and no-op commands and then try changing each one and run that until it executes. That's probably the easiest and the safest way. So, okay, so let's try this. So this is the same program from above. Was that really the same program? Yeah, it was. If we change the second last no-op, or the second last instruction to a no-op, then it completes. Okay, so let's grab our code from 4. All right, so this is our program, or this is our runner. And so we no longer really have this return condition. So, and we could have actually written this as return, I guess this is still, like, this could be while true. We could do, yeah. So we no longer have this return condition. So what we want to do is we want to, so if the step isn't seen, then we know we are broken. We are broken. So maybe return false. And then, so let's just change this to while true for now. And then if the step is the length of the program, so if it has gone past the end of the program, we want to return, return accumulator. So this is we won, we failed, or we broke. So return false. Otherwise, we're going to record it. It's still going to follow the instructions the same way. So we're going to pass in the program. We're going to run the program. And if we get a false back, then that means that the program has failed. And you know, we're going to turn this back to steps. I'm going to do the parsing outside this program. And these steps are going to, this is going to be an array. So down here, run input. So we're just going to still assert that. So something broke here. Input is not defined. Right, because we need to define the input again. It's the same input as last time. Input equals. Okay. And I'll mark this as plain. Oops. Okay, make sure that that looks okay. Gorgeous. Okay. So let's make sure that this still runs. It doesn't run. Why is that? False equals true. So this is well true. Return accumulator if step is, oh right, so because we've changed it. So let's pretend that that's still true. Return accumulator if step in scene. Okay, cool. So the code is still working the way it used to, except now we've added these new conditions. So what do they want us to assert here? They want us to assert that if we change this, that the value would be 8. So we're basically going to have a new program called I don't know, permute. And this program is going to take a series of steps, and what we're going to do is we're going to parse all the steps, and we're going to have to change. So we're going to have these, man, this is going to be annoying. So we're going to have these steps. So accumulator 1, jump 2, whatever. We're going to have all these steps. And what we want to do is we want to basically try it as is. And then if that doesn't work, we'll try it with the first jump or no op command flipped. And if that doesn't work, we're going to try it with the second jump or no op command flipped. And if that doesn't work, we're going to try it with the third jump or no op command flipped. So I guess what we'll do is we'll make a loop that goes through these steps and flips the commands and then gives us the result back. So I guess what we can do is we can say, okay, so for line in step, I guess step in steps, what we're going to do is if step dot, I guess we want to see if there's a jump or no op in there. If jump or no op. So if that has one of those commands, what we want to do is we want to replace it. So, but okay, so here's the other thing. We're going to need to track the index of that as well. So we're going to need to make a new array. So new steps equals step steps. We're going to blow that out. And then new steps, we're going to replace the line that we're on now equals, I guess we already have step, replace, we're going to replace either a jump with a no-op or a no-op with a jump. So here's another question is, we can't just replace both because it would flip back and forth. So okay, so we're gonna have to say, you know, if jump or no-op test step. Okay, you know what? If let's do this one. This one will be jump, and then we'll have else if. Oops, else if. We got language confusion. And this no-op. All right, steps replace. So we're going to replace jump with not. Jump with not. And then this is going to be not. Jump. Okay, so that's going to give us our new steps. And then what we're going to do is we're going to run new steps and say if, if we get a value, if we get a truthy value, return the value. Otherwise, it's going to continue down this line. Okay, so what do we have here? We've got permute. So it's going to go through the original array, and it's going to say, hey, if there's a jump on this line, I want you to make a new array of the steps, like a new version of the steps. And I want you to replace, on this line, I want you to replace jump with no-op. And conversely, if there's a no-op, do the same thing about replacing no-op with jump. This is like kind of repetitive, and I feel like maybe there's a better way to do this. It's not coming to me, so moving on. And then what we're going to do is we're going to return whatever running these new steps gives us if it returns a value. So if it doesn't return false. Cool. So, I mean, we can try it. Let's try it. So we want to assert 8 is permute. And that didn't just work, did it? Let's log it. Well, holy shit. Okay, well, all right. It runs our assertion. It passes our assertion. I mean, we'll give it a try. Permute and see if this is giving us an answer. No, it's not. Log permute require input. So, oh, but we need to input split. Oops. Split. 2001. All right, gave us a space odyssey of an answer. Let's give that a shot and see if it works. Submit, that's the right answer. Okay, cool. So that went suspiciously smoothly. And I'll take it, because why not? I guess what we could do is, what I'd like to do is I still feel kind of shitty about this. Don't like how repetitive this is. So what we could do is we could write a function that says, hey, if you see a jump, place it with a no-op and vice versa. Is that going to be more clear or less clear than this? We already have parse step, so we could parse the step and get the instruction back from that. So we've got that, and we don't actually care about the argument. So we've got the instruction, and then we could case the instruction. Switch when I mean, I don't feel like this is doing anything really different than what we were doing before. So what we could do is we could continue, or unless in jumper no op. I guess what we could do is we could just do that down here. We could continue. So when jump, so we're gonna create new steps. This might be a wasted operation if it doesn't contain a jump, so it might be slower. And then we got this. I mean, this isn't really, I don't feel like this is doing a lot for us. Let's see if it still works. It still works. Is this better than before? I don't know. This is still just breaking out our conditional logic. It's just putting into a switch statement instead of an if for else. And now we've got this weird continue where it's just like, hey, let's jump to the next value in the loop if it didn't match. I don't know. I find this whole thing harder to read. I'm going back. I liked it better the other way. It was nice to maybe reuse parse step again, but I find this reads better. Maybe a little spacing will help. Okay. Cool. Yeah. Yeah, and it's the same deal here with the step. So, you know, we're always adding one to the step unless it's a jump, in which case we don't add it. I mean, the alternative would be always add one to the step. And then when we're jumping, we could do -1, and that still gives us the same answer. It's a bit shorter, but again, it's like, it's not as clear. And I feel like they could add rules that would make it just more complicated, and it would become untenable to read. So, you know, it's another example where, like, you know what, there's more lines, it's more explicit, and I feel like it reads better. So, yeah, I'm okay with it. So this still works. One, I don't really feel like there's a lot to refactor here. I'm pretty happy with it. I guess the only other thing I'm not super happy is, it would be nice if we automatically split the input. And I guess we could do that. We could say step equals, whoops, or steps equals wow, steps. So if type of steps is, was it string? I mean, we could do that, and then we could throw that in here as well. That adds that, but it allows us to pass in just input, which is nice. So that still works, and the old one still works as well. So I guess that's the only thing that I would maybe do, is I would, there we go, and then this can be steps again. Wow, I can't type steps. I specifically chose steps because it would be easier to type, and I'm aware of that. Okay, 2025. Okay, all right. So I guess what we want to do now is we want to commit it. Get X. Cool. Got day 8. So that's day 8 in the bag. All right. Yeah, love to hear back if there's anything you think I could be doing better during these. I would love to hear it. Yeah, open to all constructive criticism. Either hit me up on Toronto.js Slack, or you can leave a comment below. But yeah, thanks. Looking forward to seeing you guys tomorrow. All right. And time to end the stream.